Waiting line questions aren't so much about memorizing formulas as they are about memorizing how to use formulas. I'll show you what I mean with these old exam questions. Let's look at this. All trucks traveling on I-75 south of Gainesville, Florida must stop at a weigh station. Okay. This weigh station has one set of scales which can weigh an average of 18 trucks per hour. Oh, exponentially distributed. That is absolutely perfect. That is mu, 18 per hour. We remember that mu is the traditional abbreviation for the mean of the exponentially distributed service distribution in the MM1 model. Okay, but let's read on. Trucks arrive at the weigh station at an average of 15 per hour. That is perfect. That is lambda. Lambda equals, I'm trying to write equals there, I made a mess out of it, 15 per hour. Lambda is the traditional symbol for the mean of the arrival distribution. These are the only two numbers that you need for the MM1 formulas. Now, wait, we haven't even read the question yet. What does it say? Okay, note that the formulas necessary to analyze this weigh station are included with your exam. Now, this is in your note pack, so obviously you don't have that particular page, but you would. What is it that's asked? What is the average delay a truck suffers at the I-75, okay, average delay a truck suffers at the I-75 weigh station? That is, what is the average total time the truck spends waiting and being weighed, and then a warning in minutes. Oh, all right, now we need those formulas. As a matter of fact, we actually, and this is the real challenge, only need one of those formulas. Now, we don't have that old exam page with the formulas, but we can for now get them from the book. Here it is. Here's the MM1 model. Let me make sure there's not too much glare on this page. There we go. Which one, and this is the key, which one of these do we actually need? Well, they're asking about a delay. That means a weight. That means it will be one of the W formulas. They're asking the average weight at the weigh station in total, waiting and being weighed. That would be this one, WS, weight in the system. Oh, all right. So all we have to do is fill out that formula. Now, you say, well, wait a minute, you took the book away. I didn't get the formula written down. No problem. I'll write it here. We're looking for a W because it asked for a delay, a weight, sub S for total weight in the system. And what it said was that was equal to WQ plus 1 over lambda. Now, wait a minute. WQ, that's another formula. That's the average weight the truck spends in the line, and that formula had said, oh, easy to calculate, it's just LQ divided by lambda. Oh, except wait a minute, LQ itself is another formula. That's the average, capital L for length, length of the Q, the average number of trucks in the line. That was lambda squared divided by mu times mu minus lambda. All right. Oh, and these are exactly the sort of formulas and exactly this kind of presentation, except not handwritten, you know, that you'd have on a formula sheet for your exam. Oh, all right. Now, that means that for this one question that we were asked, it's true. We really actually do have to calculate all three of those formulas just to get the one answer that we need. But no problem. Now we just put in the numbers because, let's see, starting down here with LQ, here's where we can complete this one. Because remember, lambda was 15, so that's 15 squared, and mu was 18, 18 minus 15. So I get on my calculator, that's like 225 divided by 54, or 4.1667. So we have just discovered that there's a little bit over 4 trucks in line at any given time at the weigh station, but that's not what was asked. We need that to take it over here, or you could store it in your calculator, because you divide that by 15 to get the average weight they spend in a line, 0.27778. Okay, but wait a minute. We need that to put it here, or store it in your calculator, because you tack on 1 over 18. And then finally, just this bit right here is answering the question. I get this right in here equals 0.3333, which if you look is listed right there, but don't mark it. Don't mark it. Notice that that's not the answer. But I just said that that was the answer, 0.33. Remember that whatever lambda and mu are in, when I was originally writing it down, they were per hour. That is always what your answer is in, as it's displaying on the calculator, 0.33. 1/3, 0.333333, 1/3 of an hour. Oh, right, and the question said in minutes, and the minutes had an exclamation point, like, look at that. Well, wait a minute, 1/3 of an hour, or 0.3333, if it's still showing on your calculator, times 60 minutes in an hour is 20 minutes. 1/3 of an hour is 20 minutes. Oh, all right, that's the answer to the question. Now, the second question. What is the probability that there are no trucks at the I-75 weigh station? We just have to recognize this is another way for asking for, wait a minute, where is it? Right there. P sub 0. P for probability, sub 0 for nothing, 0. The probability that there are no customers in the system, simple formula, 1 minus lambda over mu. Probability of no trucks, it's the same thing. So we just say, and maybe I can just squeeze it in here, P sub 0, 1 minus lambda over mu, which is 1 minus 15 over 18. 1 minus 15 over 18, I got 0.1667. But there it is, right there. That answers that question. Okay, now, the next question isn't a mathematical question. It's not an MM1 question. It looks like it is a conceptual question. Let's take a look. You are observing a line of people forming at the ordering counter of a Starbucks coffee on the North Campus of UB. All right. In other words, a queue. This line, or queue, has at least 15 people in it waiting to order coffee. Suddenly you notice 2 people walk through the front door of Starbucks, stop when they see the other 15 people waiting to order, shake their heads, turn around, and exit Starbucks again immediately. What you have just witnessed is an instance of customer impatience, best known as, what is the term for that? They saw the people in line, stopped, turned around, and left. That is described as balking. The test was they never joined the line, and that is very much what was described there. They just saw when they walked in the door the 15 people and they left. That is known as balking. Now the next question is also a conceptual question. Let's look. Suppose you're taking a 105-minute airplane flight from Buffalo, New York to Atlanta, Georgia. You must be flying Delta. This flight does not occur at mealtime, but the cabin staff still provide you with a small drink and 2 packs of honey roasted peanuts. You eat the peanuts and study the evacuation instructions and the airline magazine you found in the pocket of the seat in front of you. Which of the following best describes this is about the psychological modeling of waiting. Which best describes the psychological waiting principle that both you and the airline are employing to shorten this 105-minute waiting period. Because as you sit with your seatbelt on in a seat in an aircraft, that is a delay. That is a wait. Okay? Now, you are, let's think about it, bothering to browse evacuation instructions. Good for you, but also that ratty airline magazine. Why? Oh, wait a minute. Why are they handing you this pathetically small little drink to drink as well? Let's test possible reasons. In-process waits are shorter than pre-process waits. I'm going to kick that one out. That is a good principle, but in order for that to be true, there's something about the action of you reading the magazine or them giving you the little drink that would give you the impression that the service has started. You're already on the plane, you're already in the air on your way to Atlanta. It's very obvious to you that the service has already started. Okay, that principle just, it doesn't apply. Let's look at the next one. Unfair waits are longer than fair waits. That is definitely also a principle, but I'm kicking it out because fairness, the idea usually of sticking to first come, first serve, sticking to the rules, there's nothing in this scenario that's been described that has anything to do with enforcing first come, first serve. No, right? This is actually a pretty obvious scenario. The only thing that's been described here is that occupied waits are shorter than unoccupied waits. Why are you bothering with that magazine? They won't let you use your electronic devices. You're just trying to stay busy. Okay, so this is the only one that works. Let's look at the last two old questions. Oh, we're back to MM1 again. Okay, good. Let's take a look. Let me find a place to put this down. And let's look at this particular scenario. Cars traveling from Canada to the United States through the Thousand Island Borders crossing must stop for U.S. Customs and Immigration. During the stop, each passenger in the car will present a passport for inspection by a U.S. Customs officer, answer questions, and declare certain valuables which may be in the car. On average, it takes a customs officer, wait a minute, I better pay attention to this. Takes a customs officer about 5 minutes to inspect passports and release a car for entry. Okay, may come back to that. Since the Thousand Islands border crossing is not heavily traveled at night, U.S. Customs and Immigration usually keeps one lane open at the checkpoint plaza and one officer on duty processing arriving cars. Between midnight and 6 a.m., okay, really, really late, cars arrive at the border crossing plaza at an average rate of 2 per hour. What has been carefully described here is again the MM1 model. Notice we're being asked about the border crossing only after midnight but before 6 a.m., meaning there's only one lane, there's one server, and they've given us some information about how fast that one server can do things and some information about how fast cars arrive at that one lane at the checkpoint plaza. Now, what we need to do, yeah, we're just going to go back to those same old formulas and answer the two questions, is let's make sure we have lambda and mu correct. Nothing works unless lambda and mu are correct. All right, now, lambda is right here. Average rate of 2 per hour. That is perfect. 2 per hour. I saw information about mu, the mean of the service distribution, how fast a customs officer works. About 5 minutes to inspect passports. Do not write 5. Don't write 5 there. Mu does not equal 5. We need that 5. But remember that mu is never a length of time. Mu is always a number of services that can be done in a certain interval of time. It itself is never a length of time. Okay, we've been told that it takes the customs officer an average of 5 minutes. What we need to know is then on average how many services can the customs officer provide in an hour. Lambda and mu are cousins. They have to be talking about the same interval of time. We have lambda equal 2 per hour. We need mu to equal something per hour. Okay, now this is just logic. You don't really need a formula. Okay, because if it takes the customs officer an average of 5 minutes to clear a car through the checkpoint plaza, then on average, how many cars can the officer clear through the checkpoint plaza in an hour? Okay, well there's 60 minutes in an hour. And we're saying he or she will take in about 5 per car, which is just, well, revealing, so to speak, that on average, that's about 12 cars an hour. That's the number we need, the 12, not the 5. Okay? Now, having done that, now we're good to go. We're ready to go back to the formula sheet. We just need to know what formulas it is we're looking for. Oh, well, that would be the questions. Okay. Assuming this scenario meets the assumption of the MM1 model, yeah, we were just talking about that. What percent of the time is the customs officer busy inspecting the passports and from arriving cars between midnight and 6 a.m.? Oh, that one is easy. That is system utilization. That business about there's one server and what percent of the time are they busy? That's that top formula right there in the book. Lambda divided by mu. That's all you need to do. Okay, lambda divided by mu would be, in our case, lambda is 2 and mu is, careful, 12. So I get 0.11, whoops, 0.16667. Oh, about 17% of the time. Oh, wait a minute, 16.7% of the time. There we go. That's the answer right there. Then, this answer. When a car arrives at this checkpoint between midnight and 6 a.m., okay, this is while we're analyzing, what is the average length of time it must wait before speaking to the customs officer? Okay, so which of the rest of the formulas do we need? Well, it's asking for a length of time. It's asking for a wait, then it's one of the W1s. It's one of the W1s. And it's either the wait in the line or the wait in the entire system. It said before speaking to the officer, which is being served, so it must be WQ. We're looking for WQ to answer that one, which is, I was just pointing at it, lambda, or excuse me, LQ, the average length of the line, whoops, divided by lambda. Oh, wait a minute, which means that we have to first calculate LQ, which is just that lambda squared, let's see, lambda squared, this is a mu, times mu minus lambda. There. All right, I'm all set. Let's fill it in. Well, let me think. LQ, lambda was 2, so that's 2 squared, 4. And then 12 minus 2, so it's 12 times 10. So this is going to come out fairly small, 0.0333. Okay, I want to hang on to that number, like on my calculator display. Although, what is that number? That's the average number of cars that's sitting in line at any given point between midnight and 6 a.m. It's a tiny fraction of a car, right? Because it's generally, this is not a very busy time. All right, but that's not the answer by itself. That's just what we needed for right there, because we take that number and we divide it by, whoops, the lambda is 2. So that's where we get 0.0167. 0.0167, you say, oh, all right, well, that rounds to like 0.2. It must be that. Oh, except, wait a minute, this is another good reminder. It's a good practice. That's not the answer. Because this is, like I said, another good reminder. This is like the thing with the trucks. Whatever lambda and mu we're in, that's what your answer is going to be in. Let's see, it is asking for minutes. This is in hours, not hard to convert it to minutes. Just multiply it by 60. Wait a minute, I get 1. Yep, 0.0167 hours. Oh, by the way, in case anybody asks you, happens to be the same thing as exactly 1 minute. There's an average delay of 1 minute to speak to the officer.